Hello everyone, welcome back to CodeTav Management. In today's system design episode, we are going to discuss one of the most important topics in distributed systems, that is message queues and event-driven architecture. So in previous episodes, we discussed concepts such as caching, database scaling, and other important system design building blocks. And now we are going one step further. So when our system becomes large, we cannot always make one service directly call another service and wait for the response, right? So we need a way to communicate asynchronously. So that's where message queues, event brokers, pub/sub, and event-driven architecture become extremely important. So in this episode, I will explain everything using simple examples and workflows. So let's start with the very first question, like what is message queue? So let's first understand the basic concept. Like a message queue is a temporary storage or buffer between producer and consumer. So imagine we have two services. The first service is called the producer. The second service is called as the consumer. So normally the producer could directly call the consumer, but there is a problem. Like what happens if the consumer is slow? Or what happens if the consumer is temporarily down? So the producer may have to wait, or the request may fail, right? So instead we introduce a message queue. Okay. So the producer sends the message to that message queue, and the queue stores the message temporarily, and the consumer picks up the message whenever it is required. That is one kind of like swapping two numbers with help of third variable, like that. We are assigning the some value in some variable, then that again we are passing to a third variable, and then from that third variable we will pass that to the second variable, like that. So the important point here is that the producer and consumer don't have to work at exactly the same time. So for example, imagine an e-commerce application. So a customer places an order, right? The order service can publish an order created message, and the payment service can process that message later. So this makes the architecture more loosely coupled. So while showing this diagram to you, like just uh, here it is the producer. So this service creates the message. Okay. And this is the message queue. So the queue temporarily stores the message. And finally, that is the consumer. So the consumer reads and processes the message. So a message queue acts as a buffer and communication layer between services, right? I think it's clear to you now. Now next we will know like why do we need the message queues? So why can't we simply use REST APIs everywhere? There are several reasons. The first reason is decoupling. So the producer does not need to know exactly when the consumer will process the message. The second reason is asynchronous processing. So suppose sending an email takes 2 seconds. So we don't necessarily want the customer to wait 2 seconds just because an email needs to be sent. So we can put an email task into a queue and process it in the background. So that is one point, the asynchronous processing. Next is traffic spikes. So suppose normally our application receives 1,000 requests per minute. Suddenly we receive suppose 1 lakh requests. So if we directly send all those requests to a downstream service, it may become overloaded. So a queue can temporarily absorb that traffic. And another benefit is independent scaling. Okay. So if the consumer is slow, we can add more consumer instances. So queues helps with decoupling, asynchronous processing, traffic buffering, fault isolation, then we can say retrying also, and independent scaling. Okay. So a queue basically helps us build systems that are more resilient and scalable. Okay. Now we will know about what is the difference between synchronous and asynchronous communication. So this is very common system design interview question. So let's understand it with a simple example. So in synchronous communication, suppose service A calls service B. So service A waits, service B processes the request, service B sends the response. Only then does the service A able to continue. So the flow is like, see, service A to service B, then response. So the caller is waiting. So now let's look at asynchronous one. So here service A, like you can see this producer as service A. So service A sends a message to a queue and the queue stores it. And when it has been done, then service A does not have to wait for the actual processing. The consumer means the service B processes the message later. So suppose here producer to queue to consumer. So this is useful for background operations. For example, sending email, sending notifications, processing uploaded files, generating reports, payment workflows, data processing, like that. But asynchronous communication also introduces complexity as well. For example, the result may not be immediately available. So this leads to concepts like eventual consistency. So you need to use synchronous and asynchronous communication as per the requirement. So use synchronous communications when the caller needs an immediate response, and you need to use the asynchronous communications when work can happen independently or in the background, right? Next, who are producer, consumer, and broker. So first is the producer. So the producer basically creates or publishes the message. Next is consumer. Consumer basically receives and processes the message. And third one is broker. So the broker basically manages the messaging infrastructure. So it can store, route, or deliver messages. So the basic architecture is producer to broker to consumer, like that. Producer will publish the message to broker or queue, and queue will deliver the message to consumer. Okay. So like for an example, like an order service can be the producer. So Kafka or another messaging platforms can act as a broker, and payment service can be the consumer. So an important point is that one microservice can be both. Like for example, the payment service can consume order created. After payment succeeds, it can publish payment completed. So here payment service can act as both producer or consumer, like that. Like when it consumes the order created message, then it will act as a consumer, and after payment, when it will publish the payment completed, it will act as a producer. So it becomes consumer plus producer for suppose payment service, what I gave you the example. So this is very common in microservice architecture. Then what is the difference between queue and topic? So in a traditional queue model, we may have producer, then queue, then consumers. So suppose there are three consumers. Suppose consumer A, consumer B, consumer C. So if the message represents one unit of work, generally one consumer processes that message. This is useful for distributing the work. Now consider a topic. Suppose we publish order created. Okay. So multiple services may be interested on that, like payment wants it, inventory service wants it, notifications service wants it, analytics service wants it, right? So we don't want the producer to call all four services individually. Instead, we publish the event to a topic, then multiple subscriber will be there to consume it. So like conceptually, like producer to topic, and from topic to multiple consumers. Okay, so this is the foundation of PubSub. So you can think the queue as distribute work, but topic actually distribute events to interested subscribers. Okay, so here also I've written like a queue is commonly used for work distributions where one competing consumer handles a message. But for topic, one event, but there can be many interested subscribers who will consume those. So that is a PubSub architecture. Like producer will publish and subscriber will consume those. Okay. Next is what is subscribe? Like what is the PubSub basically? So this publish subscribe is commonly called as the PubSub. Okay. So that is basically a communication pattern where a publisher publishes an event to a topic. Here you can see, here one publisher will publish some event to a topic, and the publisher basically does not need to know who is consuming that event. So let's take an example, like suppose an order is created and order services publishes this order created to a topic. Okay, so now there are three services: payment service, inventory service, notification service. So all those three basically receives it. So the publisher does not directly call these all services. So this gives us loose coupling. So if tomorrow we add an analytics service, we don't necessarily have to modify order service. So we simply add another subscriber. So this is one of the biggest advantages of event driven architecture. So the publisher basically focuses on publishing the message or event, while subscribers independently decide what to do with that topic or event. Okay. Now, what is event-driven architecture? So now let's combine what we have learned. An event-driven architecture, or in short from it is EDA. Okay. So that is basically an architecture where services communicate using events. For example, order service created uh, an order, and order service publishes it like order created. Suppose this is the event broker, you can say, or you can say as a topic as well. Anything. So now several services react to this event, like payment processes the payment, inventory service reserves the stock, notification sends the confirmation, analytics records the business event. So the important thing is that order service does not need to directly call all those services. So this gives us loose coupling. So for example, if notification traffic becomes very high, we can scale notification service without scaling payment service. All are independent. So that's a major advantage of event driven architecture. So services communicate through events rather than tightly coupled direct calls. Now event versus comment. What's the difference between event and comment? So a comment is basically generally an instruction. For example, like process payment. Okay. So this means payment service like please process this payment. So a comment is directed toward a particular service or component, but an event is different. For example, like payment completed. So this means payment has already been completed. Okay. So suppose multiple service may be interested for that event. Okay. So order service may update the order status. Notification service may um, send an email. Analytics service may record the transaction. So Comment is like do something. Like here, see, this is caller, like directed that process the payment. This is a comment. Then executions will be happened via payment service. And when it is a publish to a event that payment completed, it publishing the message. And then with that message, order service and analytics service or notification service will do their particular tasks. So that is basically something happened already. So you can think that comment can be the futuristic. Like in future, the task will be completed, but there is no surety about it. But for event, means the event already has been done. It already has been processed. So it is like some past incidents happened already. So it is like you are sure that payment already has been completed. Okay. Now what should a message contain? So in a production system, we should not simply send a random JSON. Okay. So we should design a proper message structure. A message may contain like event ID, event type, timestamp, producer, uh, correlation ID, schema version, business payload, like that. Okay. So in that way, actually, and finally, the actual business payload will be also there. Okay. So why these things are important? Like why event ID is important? Because we may receive the same event twice. So we can use the event ID to detect the duplicates. Why correlation ID is useful? So it basically helps us trace one business request across multiple microservices. So for that we can use the open telemetry as well to track those things. Next is we have I have told about the schema version. Okay. So because producers and consumers may be deployed independently, so the producer may change the message format while older consumers are still running. So a well-designed message should support traceability, compatibility, reliability, like that. Next is how do we handle message ordering? So imagine we receive the events like uh, suppose three events has been already we have received like order created, payment completed, and order shipped. So they should ideally be processed in a particular order, right? Like if order shipped is processed before order created, we can have a business problem. So in Kafka style systems, messages are organized into partitions. So ordering is generally guaranteed with a within a partition. So if all events for like order ID 101, so go to the same partition. Like here I have given that partition 1. So if all events for order ID 101, so go to the same partitions, they can maintain their relative order there. Okay. So this is why keys are important. So we might use key as the order ID. If it is for order ID 102, we will go to partition 2 and there we can check particular order. So then all events for the same order can go to the same partitions. Okay. So just important interview point that don't say just like Kafka guarantees global ordering. So that is not generally correct. The practical concept is like ordering is maintained within a partition. Kafka not guarantee like the global ordering. Within the partitions, the proper ordering is particularly maintained. Okay. Now what are at most ones, at least ones, and exactly ones? So let's start with the at most ones first. So the message is delivered zero or one time. So the advantage is like fewer duplicates will be there. But the problem is that a message may be lost. At least once means the system tries to ensure the message is delivered. So if processing fails, the message can be delivered again through retry mechanisms. But there can be the problems with duplicates. For example, two times it can be happen like payment completed. So the same event might arrive twice. So therefore the consumer needs to be idempotent. Now exactly once. So exactly once like sounds ideal. Like but in a distributed system, exactly once semantics are very difficult to guarantee like across the entire end-to-end business workflow. So therefore, in practical system design, a common approach is at least once. Okay, this is the common approach. So at least once delivery with idempotent consumer. So this provides the strong practical reliability. At least once with idempotency. Okay. So what is message acknowledgement? So acknowledgement tells the broker that I have successfully processed this message. Suppose a consumer receives a message, so it starts processing. So if processing succeeds, it sends an acknowledgement as well. So the broker can then consider that message completed. But there is an important failure scenario. What is that? Like, what if the consumer sends the acknowledgement before actually completing the business operation? So suppose the application crashes immediately afterward. The message may be considered completed, even though the business operation was not completed. So that can cause data loss. So acknowledgement timing matters. So generally, we want successful business processing before acknowledging. But then another problem also appears. Like what if processing succeeds, but the consumer crashes before sending the acknowledgement? So the message may be delivered again. So that's why idempotency is so important. Okay. So we need to think in that way, like every aspect, just like before of the task completion, after of the task completion, before of the acknowledgement, after the acknowledgement, what system can behave. In that way we need to think, and in that way we need to design the system properly. Now what is an idempotent consumer? So suppose we receive, suppose payment completed, and we will get some event id. Okay, so the consumer processes it. Now because of a retry, the same event arrives again. So if the consumer process it like again blindly, we may send two notifications or perform the same business operation twice. So an idempotent consumer prevents this. The consumer can maintain a processed event store. For example, what event ID you already got, suppose this E123, that is suppose already processed. So when the same event arrives again, the consumer basically checks that event ID E123. So if it has already processed it, so it skips the business operation. So see, this is this message you got with this event ID. Okay, so it basically checks, the idempotent consumer basically checks this event ID. So if it is a new, then first time process, and if it is already seen means old, then it's a duplicate, then it will be skipped. Okay, that's the workflow. So if your message system provides at least once delivery, so design consumers to handle duplicates safely. Okay. Now, how does retry work? So retry is basically useful for temporary failures such as timeouts. Like a service may temporarily be unavailable. A network request may timeout. A database may temporarily reject the connections. So in these situations, retry can help. Like first attempt fails. Okay. So wait for a short period. then retry. If it fails again, wait longer. This is called exponential backoff. So, like attempt one fail, then it wait for suppose 2 seconds. Then attempt two fail, then wait longer, like wait for 4 seconds. Then attempt three fail, again it will wait for 6 or 8 seconds, like that. So this is actually exponential backoff. So we should also define a maximum retry count, like we should retry for 10 times or 20 times for a particular user, okay, for per day basis, like that. Or like we can set maximum retries as 3 4 something like that. So after, if we will set as maximum retries as 3, so like after 3 failures we may send the message to a date later queue, which is known as DLQ. But not every error should be retried, right? For example, an invalid customer ID is a business validation problem, so retrying it 100 times won't fix it. So we should distinguish between temporary failure or the permanent failure. Okay. So if it is a temporary failure like that, so like back off, what I have told, the exponential back off, then retry, then it can be success or DLQ. Okay. So retry is useful for temporary failures such as timeouts. Now next is what is DLQ, date later queue. So a date later queue, commonly called a DLQ. So that basically stores messages that could not be processed successfully after the configured retry attempts. So let's say a consumer receives a message, then processing fails. We retry, it fails again. We retry again. So after the maximum number of retries, we move the message to date later queue. So there is a main queue, then consumer, it will retry. Then after particular, like after maximum number of retries, we move the message to date later queue. Okay. But we need to know like why this is useful. So imagine one corrupted message keeps failing. So if we keep retrying it forever, it can consume the consumer resources and block normal processing. So a DLQ isolates that problematic message, and operation streams like can inspect the message. So they can identify the root cause. And after fixing the problem, the message may be replayed if appropriate. So DLQ is not a garbage bin. So it is an operational recovery mechanism. Okay. Now, what are consumer groups? So consumer groups are especially important when discussing Kafka. So suppose we have a topic with multiple partitions. So we have multiple consumer instances. So we can put those consumers into some uh, common consumer group. So the partitions are distinguished according to the consumer. Like those are basically distributed among the consumers. So like we can segregate in that way. Like for a partition one, it will work with the consumer one. Partition two, like topic will assign mainly partition one to work with consumer one. Then topic will assign partition two to work with consumer two. Then from topic it will assign the partition three to work with consumer three. Okay, so consumer groups are especially important when like those consumers into same consumer groups. Like suppose we have a topic with multiple partitions, what I have told here, like here we have the topic, one topic, but with multiple partitions, like partition 1, partition 2, partition 3. So we have multiple consumer instances. So we can put those consumers into the same consumer group, and the partitions are distributed among the consumers. So now the consumers can process the message parallelly. So suppose traffic increases, so we can add another consumer. But there is an important limitations. Like if there are only three partitions, then adding 10 consumer does not mean 10 consumers can all actively process separate partitions simultaneously within that group. So the number of partitions limits the maximum parallelism of the group. Like if there are three partitions, then three consumers only can do the work parallelly. So partitions basically provide the parallelism opportunity, and consumers, like consumer groups, use that parallelism basically. Next is what is Kafka partition. So a Kafka topic can be divided into multiple partitions. So think of a partition as an uh, ordered log, like partition 0, 1, 2, like that here. So this is one topic, and there are particular orders. So messages are distributed among these partitions. So why do we need partitions? Mainly for scalability, parallel processing, distributed storage. So suppose we have one partition, so processing capacity is limited. So if we have multiple partitions, like 3, 4 partitions, so multiple consumers can process them in parallel. But remember our previous questions, like where we have discussed, like ordering is maintained within a partitions. Particular order should be mentioned. So partitioning gives us scalability, but we need to carefully select the partition key if ordering matters. Like suppose order created, then payment completed, and then order shipped. Like if we will do some mistakes according to the orders, like if order shipped first, then payment completed, like that, or like order shipped then order created, that is a wrong thing. After order shipping, payment can be completed, that is a valid thing, but after order shipping, then order creations is not a valid point, right? Now what is back pressure? So back pressure occurs when the producer is faster than the consumers. Like imagine the producer generates 10,000 messages per second, but the consumer can process only 2,000 messages per second. So what happens? The queue starts growing. So this is basically back pressure. So the system needs to handle it. Like possible solution include like add more consumers. Okay. Next is like we can improve the consumer performance. We can do the batch processing. There can be like rate limit producers. Or also one possible solution can be like throttle incoming traffic, or also like increasing the processing capacity. So but we should not simply keep increasing the queue size forever. Like eventually storage and latency become problems, so we need monitoring. So important metrics include like we need to uh, like monitor the queue depth, consumer lag, processing rate, error rate, retry count, and the dead letter queue size as well. So backpressure is fundamentally a rate mismatch problem. Like producer will produce more messages, but due to the low performance of the consumer, it will unable to consume those message. Now, what are retention, like message retention and replay? So some messaging systems can retain the messages for a configured amount of time. Like suppose retention is 7 days. So why would we want this? Like because we may want to replay historic events. Like imagine we introduce a new analytics service. So instead of waiting for new events, we may replay historic events to build its initial data. Or and another example is like like recovery. Suppose a consumer has a bug, so we fix the bug. So we can replay the relevant historic events. So this is one of the powerful capabilities of event-driven systems. So however, retention requires storage, Like we need more memory to store the old events as well, right? So retention duration should be designed according to the business requirements and infrastructure cost. So if we will store more, so we need more memory, like that. So their infrastructure cost is a very important factor. What is eventual consistency? So this is one of the most important concepts in the asynchronous architecture. So let's take an order example. So suppose customer places an order, then order service immediately updates like order has been created. So then it publishes that order created, and then the inventory service basically receives that event slightly later. So therefore, for a short period, order service says order created, while inventory service has not updated yet. So this is called the eventual consistency. So the services become consistent after asynchronous processing completes. So this is not necessarily a bug, but it is a design characteristic of asynchronous systems. So, but we must understand the business requirement. For some operations, a few seconds of delay is acceptable. For others, strong consistency may be required. So, system design is always about understanding the business requirement and selecting the right consistency model. Next is what is the transactional outbox pattern. So, now let's discuss one of the most important patterns in event-driven microservices. So, imagine order service does two things. First, it updates the order database, and second, it basically uh, publishes the order created message. So there are actually two separate operations. So what if the database update succeeds but publishing the event fails? So now the order exists in the database, but downstream services don't know about the order creations. So this is called a dual write problem. So the transactional outbox pattern basically solves this problem. Like whenever one interviewer will ask you some pattern or something like that, you need to tell what was the problem, and to solve that problem, basically that pattern came into picture. So I have discussed about the problem first, that suppose order creations happened in the database, and then the message that order creations, that message generations has been failed or message publishing has been failed, then the downstream service will not able to know about it. So that is basically dual write problem, and to solve that dual write problem, basically that transactional outbox pattern came into picture. So instead of immediately publishing the event, the service writes the business data and outbox record, so inside the same database transaction. For example, suppose there is a order table and there is order ID like 101, like that. And in the outbox table, there the event will be generated as order created. So both are committed together. So this transaction and this transactions. So here the in the order table, the order ID will be created, and that is the outbox table. So outbox table, the event order created, that message or event will be published. So two transactions will be happened parallelly and committed together. So then a separate publisher reads that outbox table and sends the event to a message broker. So just think like that. Service, then from service, two transactions happened. One is to the database, like the order table where the business data will be stored, and another transactions here, the outbox table. Then there is a separate publisher that will read the message from the outbox table, and then the publisher will publish the message to the broker. Okay. So if an interviewer asks like how do you guarantee that a database update and this event publication don't become inconsistent, like how you guarantee that those two are consistent? So the strong answer will be like, I would consider the transactional outbox pattern. If you will tell that, the interviewer will also able to know that you know about this. But yeah, suppose the interviewer will ask you first of all this question, like, suppose there is a service, and from that service, like, two transactions happened. One, like, there the business data will be stored in a order table, and there is a outbox table. There the outbox, like, the event will be published. Then how will you guarantee that those two will be consistent manner? Then you need to explain this architecture properly, this design flow properly. Then you need to tell properly that I will implement the transactional outbox pattern. And there also you need to explain what is the transactional pattern, outbox pattern is, what was the dual write problem. Okay, so those things you have to explain, like, as those are both the transactions are parallelly. So through the transactions, if those are not committed, then again those will be rolled back. Okay, so if those will be failed, then this process will not be completed. So when those two things will be, like, this business data will be created in a business like order table, and the event will be published in that outbox table, then that we can consider the transaction will be completed, not earlier than that. Okay, how do you design an e-commerce event workflow? So suppose we are designing an e-commerce system. So the customer places an order, the request goes to the order service, and order service creates the order, then it publishes the order created. Now the event goes to our event broker. So multiple services will consume it. First, see, payment service. So it processes the payment. Second is inventory service. So it reserves the product. Then is notification service. It sends the confirmation to the customer. Next is analytics service. So it records the business event. So our architecture will looks like that: the customer, then order service, then broker, event broker, and then uh, payment, inventory, notification service, analytics service, who will try to subscribe that event. So order service does not need to synchronously call all four services. So each service is independent. So if notification service is temporarily unavailable, it does not necessarily mean the entire order creation request must fail. The notification event can remain in the messaging system and be processed later. So similarly, payment and inventory can scale independently. So we can also add retry mechanisms, dead letter queue, idempotency, consumer groups, partitioning, monitoring, transactional outbox, whatever we have discussed. So just let's quickly summarize the entire episode 10. So a message queue gives us a buffer between producers and consumers. Then we have discussed about asynchronous communications, right? So that basically allows services to work independently. Then PubSub basically allows multiple services to react to same event. Then event-driven architecture basically uses event to reduce the direct coupling between services. Then partitions basically provide scalability and parallel processing. And for one Kafka topic, there can be multiple partitions, and according to the partitions, each consumer instances will be allocated, and through the partitions we can able to know how much work can be parallel. Next, consumer groups allow multiple consumers to share the workload. Then we have discussed what, just date later queue have told, consumer groups told, back pressure is there, we have discussed. We have also discussed the acknowledgement, right? Anyway, yeah, so here see the acknowledgement. So acknowledgement basically tell the broker that processing is succeeded. And then also we have discussed about at least once, exact once, like that. So at least once delivery can result in duplicate message. Therefore, we need idempotent consumers. Then retries handle temporary failures. Hmm. Then dead letter queue have discussed like dead letter queues basically isolate messages that repeatedly fail. Then we have discussed the back pressure. So back pressure occurs when like producers are faster than the consumers. Then retention and replay. So those basically allow the historical events to be processed again. Then eventual consistency. So eventual consistency is an important characteristics of many asynchronous systems. And finally, we have also discussed about the transactional outbox pattern, right? So that basically helps to solve the database and event dual write problem. So if an interviewer asks you like how would you design a scalable event driven microservice architecture, so you can answer like I would use an event driven like an event broker between loosely coupled services. So producers will produce the message or like publish the business events and consumers would process them asynchronously. And also you can tell like I would use partitions and consumer groups for horizontal scalability, retries and DLQs for failure handling, idempotent consumers for duplicate messages, appropriate keys for ordering and monitoring for consumer lag and queue depth, and for like reliable database to event publishing. And I would consider the transactional outbox pattern. I would also explicitly define the consistency and delivery guarantees required by the business. So that answer demonstrates that you are not just familiar with the Kafka or Q as technologies, you understand the system design principles behind them. So that's it for episode 10. So in this episode, we have covered all those concepts like message queues, asynchronous communication, PubSub, event-driven architecture, Kafka partitions, right? We have discussed all those things, right? And also we have discussed like idempotency, back pressures. So these all concepts are extremely important when designing scalable microservices and distributed systems. So if you are preparing for Java, Spring Boot microservices or system design interviews, just make sure you understand these concepts, not just theoretically, but also through architecture workflows where you need to use what according to the business scenarios. So thanks for watching CodeTav Management. See you in the next system design episode. But do like, share, and subscribe for motivating me. Thank you, everyone. Bye.